Okay, so hello and welcome back. So the next thing that you need to know about these transistors is basically, suppose that you have an NPN transistor, for example. So an NPN transistor, as we discussed in the previous video, is a cathode of a diode connected to basically again the cathode of a diode, and this is basically this becomes your base, this becomes your collector, this becomes your emitter, right? So if you think about only the base emitter basically diode here, you can of course forward bias this diode, meaning that if you connect the anode of the diode to a power supply, to the positive pole of a power supply, and the cathode to the negative pole of the same power supply, then of course this diode would be forward biased, and then the current would be going through this circuit in this direction, right? And of course you can use some resistor over here in order to basically to limit the current, and then this would be the base emitter diode of the transistor is forward biased, and the current is going through your circuit. So the same thing basically I can show it this way, or I can put the resistor up here, and then instead of basically these two diodes and the whole business over here, I can simply draw a transistor over here, something like this, and then this would be my base, this would be the collector, then this would be the collector, and this would be the emitter. And so if I put this resistor over here and then connect this to the power supply like this and like this, and then put the emitter, connect the emitter over here, so then this diode would be forward bias, and then the same thing would of course happen over here, and then the current would be flowing in this circuit, meaning that the base emitter diode would be forward biased. So that's something simple, of course, that you can understand, and you can see that you understand that essentially based on the fact that you know that the base emitter diode of this transistor is essentially a diode in this direction, and so you know that basically which terminal to connect to positive, which terminal connect to negative, because you know that this is cathode, you know that this is anode, and so on and so forth. And of course you know that this is an NPN transistor, right? Otherwise there would be no way to know what to do here, of course, and then you would have to essentially memorize the whole thing, and I don't really think that memorization will help that much, because there is a whole lot of material here to learn, and if you keep memorizing things, after a while you will probably forget everything. Now of course whenever you connect something to a power supply, then you essentially need to be able to do a couple of calculations. Now suppose that you have the same circuit over here, meaning that suppose that you have an NPN transistor over here. This is the collector, this is the emitter, and this is an NPN transistor. And suppose that I connect this to a resistor over here, to the positive pole of a power supply over here, to the negative pole over here, back to the emitter, the same thing. And suppose that my power supply is 3 volts. And suppose that this is a 1 kilo ohm resistor, and of course, if I do this, then of course there would be some current going through this circuit, which is I, right? And of course I can call this I of B because this is basically essentially the base current of the transistor, right? Now, in order to calculate the base current of this transistor, basically when it comes to transistors, it's not easy to see what the transistor is going to do, because it's a semiconductor junction, and the semiconductor junction is not something linear. It's always it's always a curve, depending on the different values of the independent variable. Then the dependent variable is going to have different values for, and it's essentially the graph is always going to be a curve, meaning that at different values you don't really know what to expect, although unless that you really know how for example that particular device behaves. So I'm not going to be so I cannot really depend on this diode over here. I have to somehow figure out this current based on the resistor that I have here. And of course I have put this resistor over here for the exact same purpose, in order to have some control over the current that basically the base emitter current of the transistor. Otherwise I wouldn't have put the resistor over here in the first place, right? Now, in the forward bias diode that we talked about in the previous video, we said that basically if you connect a power supply to a diode like this, then you can put the resistor over here, and this is positive, so this becomes the anode of the diode, and then the cathode goes to negative. And this is a forward biased basically diode, and of course current is going to be going in this direction. This is positive, this is negative. Now we said that the graph of basically current versus voltage of this forward bias diode is essentially something like this, meaning that if I take this as if this is voltage and if this is current, then basically the current is going to rise only if the voltage is less than or is greater than or equal to basically 0.7 volts, and it's essentially going to behave something like this, meaning that there is a 0.7 volt voltage drop across this diode before the current can start rising in the circuit. And so that 0.7 volt is going to be dropped over here. So your power supply voltage is 3 volts. 0.7 volts is going to be dropped over here. That means that the voltage drop across this resistor is going to be 2.3 volts. Is going to be 2.3 volts across this resistor. So now you can simply use the Ohm's law in order to calculate the current going through this resistor, and that is basically, you know, that V is equal to IR, and of course I'm not doing any of this. This software is doing a couple of things sometimes that I don't really expect. So I know that V is equal to IR if I use the Ohm's law only for this resistor, I would get basically the voltage across the resistor is 2.3 volts is equal to I, which is basically what I want to calculate, times R, and the resistance is 1 kilo ohm, which is 1000 ohm. So then I would be equal to basically 1000 divided by 2.3, 1000 ohms divided by 2.3 volts, and that would be something like, I don't know really, so 1000 divided by 2.3 volts would be 434. No, I'm sorry. No. Made a mistake here. 400 amps. I is equal to basically 2.3 volts. 2.3 volts by 1000 ohms, which is the same thing as 2.3 divided by 1000, which is the same thing as 0.023. I take two significant figures, for example, so it becomes the same thing, 0.0023. 0.0023 amps, which I can write as basically I can write this as 0.23 into 10 raised to the power negative 3 amps. I'm sorry, 2.3, which I can write as 2.3 into 10 raised to the power negative 3 amps, which is the same thing as 2.3 milliamps, right? It's 2.3 milliamps. So that means that the current going through this resistor is 2.3 milliamps, and then of course, since this is a series circuit, the same current is going through the base emitter junction of this transistor through the power supply and back and forth and so on and so forth and over again, right? So that's one typical thing that you need to be able to do in the case of these circuits. You need to be able to calculate the I of B, or the base current of your transistor. This is how you calculate the base current of your transistor. And you need to pay attention to the fact that over here my voltage, my power supply voltage was only 3 volts, right? Now let's see what happens if I change the power supply voltage, if I increase the power supply voltage to 10 volts. Let's see what happens there. If I have the same circuit over here, meaning that if I have an NPN transistor here, and if I connect this through a resistor, if I connect it to a power supply positive and negative to basically to emitter to negative, and if this is 10 volts, and if this is again the same thing, 1 kilo ohm resistor, and then basically there is a voltage drop of 0.7 volts here. Let me restart this software. Okay, I hope that now the problem has been solved. So basically now the power supply has been increased to 10 volts. The resistor is 1 kilo ohm, and there is still the same voltage drop across the base emitter junction of the transistor, which is 0.7 volts, right? Now, since the power supply voltage, now in the previous example that we had here, what I did was that basically, since this is a series circuit, you have essentially, if you think of this, if you think of the base emitter junction of the transistor as a resistor, for example, as some load, for example, and you have the resistor over here, and then that's connected to a power supply, right? So this is the 1 kilo ohm resistor, and this is the base emitter junction of the transistor. So of course you know that in a series circuit, the voltage drop that you have here, then the voltage drop that you have here, when you add them together, you will get the power supply voltage. So, and then based on this, I knew that there would be 0.7 volt voltage drop across the base emitter junction of the transistor here, and so I subtracted this voltage from this voltage, and then I got the voltage drop across the resistor, and then based on that I used the Ohm's law in order to calculate the current for going through the circuit. Now if I do the same thing over here, basically of course I can do the same thing over here, meaning that I can say that basically there is 0.7 volts voltage drop across the base emitter junction of the transistor, and so the voltage drop across the resistor is going to be 9.3 volts, for example. So I can say that V of R, for example, is 9.3 volts, and then your basically the resistor itself is 1 kilo ohm, and therefore basically I know that V is equal to IR, so basically 9.3 volts is equal to basically I times 1000 ohm, and so I is equal to 9.3 volts divided by 1000 ohm, which is equal to something like 9.3 divided by 1000 would be, of course, it would be 0.0093, right? Would be 0.0093 0.0093 volts, and so I'm sorry, not volts, but of course in amps. That would be in amps, and and of course here I'm supposed to actually round to one significant figure because of the fact that I have one significant figure. I don't have more than one significant figure here, so I actually have to write this as 0.009 basically amps, right? Which is the same thing as basically 900 milliamps, or 9 milliamps actually, 9 milliamps, right? So this is 9 milliamps. So now this is basically provided that I basically subtract the voltage drop across the base emitter junction of the transistor from the power supply, and then based on that I get the voltage drop across this resistor, and then based on that I calculate the current going through the circuit. Now suppose that I don't actually do that, meaning that I don't take into consideration the voltage drop across the base emitter junction of the transistor. Let's see what happens there. So if I assume that the voltage drop across the base emitter junction of the transistor is just not there, meaning that it is 0, then all of the voltage would be dropped across this resistor, meaning that V of R would be equal to 10 volts, right? And R would be equal to basically 1 kilo ohm. And so since V is equal to I times R, then V, which is basically 10 volts, would be equal to I times basically 1 kilo ohm, which is basically which is the same thing as 1,000 ohms, and so I would be equal to 10 volts to 1,000 ohms, right? 10 volts to 1,000 ohms, and that's the same thing as 1/100th of a. That's the same thing as basically 10 to 2,000 is 1 to 100, and that's the same thing as 0.01 amps, right? Which is the same thing as 10 milliamp, right? So now, as you can see over here, the current that I calculated was 9 milliamp, and the current that I calculated here was 10 milliamp, meaning that there is only 1 milliamp difference between the current that you calculate there. So there is not much. I mean, you don't really have to take into consideration the voltage drop across the PN junction or across the base emitter junction of the transistor. If your power supply voltage is at least 10 volts, then you don't have to take into consideration basically the 0.7 volts voltage drop across the PN junction. You can just simply ignore that, because relative to the supply voltage, this can be ignored, right? And as you can see in the calculation, you can see that the difference is only, for example, 1 millivolts, which is basically in most cases it can really be ignored, because you don't really need in most cases you don't really need that much precision or in your calculations, because you already have much less precision in your circuits anyway, because of all of the tolerance with your resistors and all of the other factors that come into play when you basically do anything with electronics. Then of course the PN junction is not supposed, the voltage drop across the PN junction can actually be ignored. If your power supply voltage is 10 volts or above, then it doesn't really matter how much the voltage drop across the PN junction. You can just simply ignore it, right? Okay, so that's again another example of calculating the current, the base current of your transistor, right? So now one more thing that you need to be able to do with these transistors is to calculate the collector current of the transistor, which is also important, because ultimately this collector is going to be connected to something, otherwise it wouldn't be there, right? So we need to basically start doing some calculations related to this collector as well. So now let me take a few minutes rest, and we will do a couple of calculations with the collector as well. Okay, so now if I use the same transistor the same NPN transistor, meaning that I have the cathode over here of the diode, and then another anode over here, another cathode over here, and so on and so forth. And basically connect this, and this becomes your base, this becomes your collector, and this becomes your emitter, and this would be basically an NPN transistor. So now you can see that basically now you have a diode over here, you have a diode over here. If I connect this, suppose that I connected this, for example, put the resistor over here, and I connect the power supply over here, and put a power supply and connect this back to this diode. What happens is that basically the positive pole of the power supply is connected to cathode, which means that this diode is now, and then ignoring this diode for now, the positive is, the negative is connected to the anode of this diode, which means that this diode is reverse biased. Since this diode is reverse biased, of course, no current can be flowing in this circuit. On the other hand, this diode, in the case of this diode, if I ignore this diode for now, the positive is connected to anode, negative is connected to cathode. This bias is forward biased, and current would be flowing through this diode, but then again, since this diode is put in series with the circuit, of course there would be no current flow in this circuit, right? Now suppose that I do the, basically I have the same circuit again over here, meaning that the cathode and then again another cathode over here, and then this time I connect the same power supply over here, meaning that I put the resistor over here, and positive over here, and negative over here. So this is positive and this is negative, and so this is your collector, this is your emitter, and this would be your base. But then this time what I'm going to do is that I'm going to connect the base also to a power supply as well, meaning that I put the resistor over here, and I'm going to forward bias this diode, meaning that I connect this to positive and this to negative, and connect this over here. Now what happens over here is that what happens internally in the transistor is that there is basically there is something that happens in this region of diode of the transistor, meaning that the transistor of course is NPN. So you have some P material over here, you have some N material over here, some N material over here. This becomes, for example, your collector, this becomes your emitter, and this becomes your base, right? So the base emitter part, when you connect it when you connect it to a power supply like this, meaning that when you forward bias this diode over here, and of course you can imagine that there is some resistor over here as well, then basically current can be flowing between the collector and the emitter, meaning that then you can connect the collector to a power supply like this, and put this over here, bring this over here, and suppose that you have some resistor over here as well. And in this case, what happens is that something happens in the sandwich region between the basically in this region over here. There is something that happens that the current can then flow in this circuit in this direction, meaning that the current can go from in this direction over here, meaning that from positive to negative, of course, or essentially from here. Basically, this would be the collector current of your circuit and this would be the base current of your circuit, I of B, right? So that means that whenever the base current is flowing in the circuit, the collector current can actually flow in the circuit, meaning that since there is the base current going in this direction, then the collector current can actually go in this direction, I of B. The collector current can move in that direction, I of C actually. I of C can go in that direction. And I of B and I of C, right? So that's basically how a transistor works, meaning that provided that you have the base current going on, the collector current can be flowing in the transistor, and then the problem that basically one of the diodes is reverse bias would be taken care of by the internal workings of the transistor, and then the transistor will allow the collector current to be flowing in the circuit, right? And so in short, you can say that whenever the base current is flowing, the collector current can actually be flowing, provided that you basically connect your transistor to a power supply in this manner, meaning that basically you have a transistor like this. This is an NPN transistor, and you connect this to a power supply like this, positive and negative, and then the emitter is connected to negative, and then you can connect a positive to the collector, as you can see here, and then the negative over here, and then basically there will be a current going through this. I of C would be flowing in this direction, and I of B would be flowing in this direction, and that's basically an NPN transistor, and how you can actually turn the transistor on. Of course, the transistor is not fully on, but there is some current basically related to your I of B, and there is some current related to your I of C, and then we will see in the rest of these videos how you can fully turn on your transistor, right? So that's basically one thing, and so basically what you can say is that the base current is causing the collector current to flow, right? So the collector current can flow as a result of the base current flowing, or the base current is causing the collector current to flow. And that's basically the whole story here. So the PNP transistor is again the same story, except that you have to turn the whole thing around, meaning that positive becomes negative, negative becomes positive. but as long as you remember the direction of these diodes, it's easy to do this, to draw the circuit on your own, meaning that, and let me do a PNP transistor as well. I don't know what happened to. Okay, so a PNP transistor, you essentially have the p-type material, which is basically the anode of a diode over here, and then the cathode, two cathodes are connected together this way, and then you have the anode this way, and then this becomes your base, right? So then essentially you want to forward bias and so this is your collector, this is the emitter, and this is your base, right? Essentially you want to forward bias the base emitter junction. So to forward bias the base emitter junction, you can simply put a resistor over here, and the cathode is supposed to be connected to negative, the anode is supposed to be connected to positive, and now you have forward bias the base emitter junction of your PNP transistor, right? And basically current is flowing in this circuit, in this direction, I of B, right? And of course you can see that basically the battery is, or the power supply is compared to the NPN transistor, is connected in the reverse direction, and the current is, of course, as a result, is flowing in the reverse direction as well, but it's basically the same principle. And of course you can do the same thing over here as well, meaning that in the case of the NPN transistor, we connected the collector to positive. Now we are going to connect the emitter to positive, meaning that I'm going to put a power supply over here, connect this to a resistor, and negative and positive, and then connect this to positive, and this is negative, and then the collector current is going to be, I of C is going to be moving in this direction, right? So that's basically a PNP transistor. Essentially you are moving the whole thing around, and you can draw it this way as well, meaning that this would be a PNP transistor. The arrow is basically inwards, and then you have basically your base is connected to a resistor, and then to a power supply like this, and then your emitter is connected to the same to positive here, and then your this is your emitter, and then your collector is connected to a resistor here, to a power supply, and positive, and then this is a PNP transistor. This is your R of B, this is your R of C, this is your I of C, this is your I of B, and that's basically the whole story. So that's a PNP transistor, right? And again, the same principle works here, meaning that the base current is causing the collector current to flow in the circuit. Otherwise, if you didn't have the base current, you would not have the collector current flowing in the circuit, right? Now from this point onwards, because I don't want to confuse you with PNP and NPN, I'm going to basically concentrate on the NPN transistor, because you already now know basically what is a PNP transistor, the diodes, you know in which direction to use the diodes. And so whenever you need a PNP transistor, you can do the schematic based on what you can see right here, right now. But otherwise, from now on, we are going to talk about exclusively about a PNP, an NPN transistor. And then again, basically, of course, these are not really that necessary, but if you have an NPN transistor, basically you have a power supply over here. So basically what you do usually is that you usually put the basically you have a transistor, or you have an NPN transistor over here, for example, and then you have your base connected to a resistor, and then connected to a positive power supply, and then the negative is connected to the emitter, and then you have another power supply over here. You have another power supply over here, basically some resistor over here, and another power supply over here, and then this is positive, this is negative. What you usually do is that you use only one power supply for the whole circuit. This is an NPN transistor, meaning that what you do is that you have your NPN transistor like this, and you have your base over here connected to the power supply like this. So this is positive and this is negative, and basically, and then what you do is that you connect your collector over here and bring it and connect it to the same power supply over here. This becomes your R of B, this becomes your R of C, and this becomes positive and negative. And as you can see, your collector is now connected to positive, which is the case here, through this resistor, and then your emitter is connected to negative, which is again the case here, and then your base is connected to positive, which is again the case here. So everything works out fine. So you don't really need two different power supplies for the same transistor. One is enough, right? And then the base current basically goes through from the power supply through this resistor, and then through the PN junction, the base emitter junction, and then back to the power supply. This is your I of B. And then your collector current goes from the power supply back here through this resistor, and then through the transistor back out of the emitter, and then back here to the power supply. So this is your I of C, right? So that's basically how the current is flowing in your circuit. So that's basically the simple things that you need to know about these NPN and PNP transistors, and how you basically connect them to a power supply. And the same thing that we did here, you can do for the PNP transistor, meaning that instead of using two separate power supplies, you can essentially use the same power supply for the collector current, also for the base current, right? Okay, so in the next video we will talk a little bit about Okay, we will talk a little bit about H of Fe, or the beta, or the collector gain of the current gain of the transistor. So I'll see you in the next video, and thank you.